Hello class, hope you all are doing well. We are going to talk about chapter 8, quantities in chemical reactions. The purpose of this chapter, we are going to find out if we have 10 grams of reactants, how much of products can be made. So relationship between amount of reactant and products. If we are going to have 20 grams of products, how much of the reactants are required? So there are general questions that we need to answer by this chapter. That is why this chapter has this title, Quantities in Chemical Reactions. We are going to talk about amount. We have one specific terms regarding this study, this concept. We call it stoichiometry. Stoichiometry, it consists of two Greek terms, stoichion and meter, and we are going to measure relationship between reactants, products, or any two types of species in chemical reactions when we work with the numbers. So I'm going to talk about this concept by more details and examples. First, let me define one concept in the chemistry. We call it mole ratio. As you see here, based on this definition, let me put this window here. It says the ratio or conversion factor between any two species in a chemical reactions. Any two species in the chemical reactions. It means it doesn't matter we have them as a product or reactant. If you pick any of two, it would be called mole ratio. Let me give you one example here. Assume that we have this reaction. Two hydrogen gas react with oxygen gas to produce H2O liquid, 2H2O liquid. You may pick any of these two, or hydrogen and water, to write the conversion factors. Whenever you are going to write the conversion factors, you may write two types of conversion factors. The first part is, for example, here I'm going to write between the hydrogen and oxygen. I'm going to write conversion factor or mole ratio between these two compounds, H2 and O2. H2 and O2, they are two substances that we are going to write the mole ratio. You may write 2 moles H2 on the top and 1 mole O2 on the bottom, or vice versa. 1 mole O2 on the top, 2 moles H2 on the bottom. We write this quantity and unit for conversion factors, 2 moles. So it means we interpret these numbers as a mole. We should say 2 moles H2 plus 1 mole O2 to produce 2 moles H2O. So the numbers we report always as a mole. 2 moles, 1 mole. 1 mole, 2 moles. If I'm going to write relationship between this one, H2 and H2O, only these two, the first reactant and the product, I should say 2 moles H2 and 2 moles H2O, or vice versa. 2 moles H2O, 2 moles H2. And you may write for any combination of elements, compounds, or in general substances in chemical reactions. So we have this definition. The mole ratio can be used as a conversion factor to convert between moles of one substance and another one to another one. We have questions like this. If we have this balanced reaction, so we need to always have a balanced chemical reaction, a balanced chemical equation. If 4 moles of oxygen are present, 4 moles of this present, how many moles of H2 could be formed? How many moles of H2? So look here, I give you information of one substance and I ask you information of another one. This is the object of the stoichiometry calculation. So whenever we are going to work on the problems like this, we should know what type of substances we are looking for. Oxygen, this one, and H2O, that one. So we don't work with H2. We never look at the H2. We always look at these two. Before working on the problems, we should make sure we have a balanced chemical equation like this one. When we have a numbers as a coefficient, it means we have a balanced chemical equation. So we start with original numbers and quantity given, 4 moles of oxygen. We write 4 moles of oxygen. I'm going to write conversion factor. What do you think if I'm going to write in denominator on the bottom of the fraction? I have to write moles oxygen. So I should write this one again here, moles oxygen on the bottom. I'm going to find for H2O, so I write moles H2O on the top. Relationship between O2 and H2O, mole and mole. Always we report like a mole. So we should look at the numbers. 1 mole O2, as you see here, 2 moles H2O. So whenever I'm going to write the conversion factor like this, I need to look at the balanced chemical equation. We started with this one. We write moles O2 bottom and moles H2O on the top. 2 moles for water because of 2 here, and 1 mole for oxygen because of 1 oxygen here. Moles O2 and moles O2 cancel out, so you just need to multiply this one. You have 2 suffix to report your final answer. We call this one mole ratio or conversion factor. This type of problem, this type of stoichiometric problem, we call them mole calculation. We are given moles and you are asked about moles. Mole calculation. I may ask you to pause this video and look at this example and see are you able to solve that one, and then I explain for you. Look here, for this question it says how many moles of carbon dioxide will be produced by the reaction of 2 moles of glucose with oxygen. So we should find this relationship between glucose, this formula, this is one type of sugar, and CO2. For this one, we should start with this original number, 2 moles glucose. And we are going to convert moles glucose to moles CO2. I'm going to write conversion factor. So I should write moles glucose on the bottom, and we are going to find moles CO2. The conversion factor we are going to find 1 mole for glucose and 6 moles for CO2. We don't look at the oxygen and H2O here. So moles and moles cancel out. 2 suffix, we should report by 2 suffix here. We use this mole ratio between CO2 and glucose. 6 moles CO2, 1 mole glucose. So non-substance is given in moles, desired substance is requested in mole. Mole calculation. And this is the final practice for mole calculation. I may ask you to work on that and see are you able to get the correct answer. Here it says how many moles of aluminum are produced if we have 0.5 moles of O2. So how many moles of aluminum, question mark, when we have 0.5 moles of O2. To get the answer for this one, we start with 5.5 moles of O2. 0.5 moles O2 multiplied by, we should write moles O2 on the bottom, and we have moles aluminum on the top. Look at the numbers for aluminum, 4. Look at the numbers for oxygen, 3. So moles oxygen cancel out. 1 suffix, we should report by 1 suffix. So if we are going to report by proper suffix, we should say 0.7. So we should say 0.7. I have to correct that one. We should report by 0.7. I'm going to talk about another type of stoichiometric calculation. We call it mass conversion factor, or whenever we have amount of the compounds, substances in grams, kilograms, pounds, or any units in mass. If we are going to do that, we need to have one of the conversion factors we learned about it in chapter 6, molar mass. If you remember, mass of 1 mole substance. So we need to have relationship between grams and mole, relationship between 2 different units. It's a conversion factor. Conversion factor means we are going to convert 1 unit to another one. When we say molar mass, we are talking about the mass of 1 mole. So we are talking about relationship between grams and mole of one substance. So we need to have that one. So always you have the periodic table and you are able to calculate molar mass of any substances. So one of the conversion factor for this type of stoichiometric calculation is molar mass. Always you have access to the periodic table and you can calculate it. So whenever we are going to work on the molar mass and apply that one for our problem solution, first we need to know that when we say mass calculation, we have mass of one substance and we are asked about mass of another substance. Let me give you one example. We are going to say if we have 2 grams aluminum, how many grams of aluminum oxide are produced for reaction of aluminum with oxygen? This is a reaction. This is a chemical equation. When you work in your real chemistry or real life, if you are going to cook something for your party, your event, your guest, if you have 10 guests, 10 friends invited to your place, so you are going to know how much of the material you do need to make the cookie for your friends. So this is the example we have in our daily life. So whenever we are going to do that, first in the chemistry, we need to convert mass to mole. The only way we can convert mass to mole is molar mass. Look at the terminology, we are going to convert mass to mole. We call it molar mass. Then you are going to convert mole to mole. We need to look at the balance reaction, and whenever you are going to convert mole to mass, we need to look at the molar mass again. Mole to mass, we call it molar mass. It looks we need to use molar mass twice and balance equation once. Mole ratio. So for mass calculation, we have 3 conversion factors. So let me work on this example. It says how many grams of HNO3. What is the name of that compound? Is it acid? Is a polyatomic acid? So we should write the name like nitric acid. So how many grams of nitric acid are required to produce 8.75 grams of N2O? What type of the compound do we have? Can you be able to identify this compound? N2O, 2 nonmetals. So we should use the prefixes. Dinitrogen monoxide. So dinitrogen monoxide is the correct name of this compound. So 2 substances, HNO3, N2O. So I need to work with HNO3 and N2O. 8.75 grams for that, and we are going to know how many grams. Whenever we are going to do that, we have like this solution map. Grams of this compound given. We need to convert it to moles. The only way gram to mole, we call it molar mass. Then the only way we can compare and convert one substance to another substance is mole. So we should write moles N2O and moles HNO3. And then we need to convert moles HNO3 to grams HNO3. It means mole to mass. We call it molar mass. The conversion factor we need to use. We are going to start with 8.75 grams N2O. So I should write N2 on the bottom, and we are going to convert to moles. You need to calculate molar mass of N2O. Look at the periodic table. Based on the strategy we applied in our class, you should find the molar mass. Always 1 mole. Whenever we have molar mass, always we write 1 mole. And we have like this. Grams and grams cancel out. So we use this conversion factor. Molar mass of N2O. Next conversion factor, we are going to convert moles N2O, moles of this substance, to moles of another substance. The only way we can do that, look at the balance equation. I am going to write moles N2 on the bottom and moles HNO3 on the top. The numbers here comes from the balanced equation. 10 moles for HNO3 and 1 mole for N2O. So this is the mole ratio. Always whenever we are going to convert one substance to another one, we use the mole ratio. So mole and mole cancel out. Right now I have moles of this compound. I'm going to convert to moles of another one. So as you see here, I need to convert moles to mass. So we call it molar mass. So I should write moles HNO3 on the bottom, mass on the top. Molar mass always one for substance and another one mass for that one you should calculate. So whenever we have any mass calculation, you need to calculate molar mass of substances. One for the first one for another one. And also you need to have mole ratio of them. If you calculate that one, I am going to give you the correct answer. 36 and 36 reported for this example. It means if we start with 8.75 grams, this compound, at the end we are able to make this amount of nitric acid in our lab when we work in the real chemistry or practical chemistry. Same like this, it works in our class. I'm going to talk about stoichiometric calculation in our real worlds. If we look at the textbooks and also some resources, always you have examples regarding the cooking, always. So I'm going to show you the cooking example as well as this example that you see here. The example, it says, if we have this general information, 2 wheels and 1 frame, they make 1 bike. By these 2 materials, we can make 1 bike. A couple possible questions. How many wheels and frames do you need to make 5 bikes? The strategy you use to answer this question, we call it stoichiometry in the real world. How many wheels and frames do you need to make 5 bikes? So I need to have 5 bikes. It means I need to have 5 frames. It means I need to have 5 wheels. So the answer, 5 times 2, 10 wheels. So the answer is 10 wheels, 5 frames. We can make 5 bikes if we have this material. 10 wheels, 5 frames, and 5 bikes. But if we change the level of our question, if you have 6 wheels and 4 frames, how many bikes can you make? Think about that and see, are you able to get the answer? If you have 6 wheels and 4 frames, how many bikes can you make? The strategy you use to answer this question, we call it stoichiometric calculation. If we have 6 wheels, it means we need to have 3 frames. So we have 4 frames. So for 6 wheels and 3 frames, we can make 3 bikes. But we have 4 frames, 1 extra, but we don't have any more wheels. Whenever one of the material, one of the reactant completely gone, completely consumed, we call them limiting reactants. In this example, we have 1 more frame, but we don't have enough wheels to make more bike. So we call wheels are here, they are limiting reactants. And we have 1 more frame left over, one more flame. We call it additional reactants, or in textbooks we call it excess reactants. So 2 terms, limiting reactants, excess reactant. If reactants completely consumed, completely gone, there is nothing there, we call it limiting reactant. If we still have some materials but we don't have other materials to react and we can't use them, we call them leftover excess reactant. So I'm going to give you example you see on your textbook. Your textbook talk about the pancake, making pancake, but here I'm going to talk about the burgers. Assume that we have a simple recipe to make burgers. How many burgers can we make? So it depends on the amount of the reactants, it depends on the amount of the material we are going to start with them. We have some limiting reactant. So for this example, we may consider the lettuce. If we are going to have a pair lettuce for each one, they are limiting reactant, and we can make only 3 burgers. So here, other materials are left over. We call them excess reactants. So Another example to make sure everyone can get that, if we have 8 car bodies and for 8 tires, we can make 8 cars with tires and 16 tires in excess. Tires, 16 tires, we call them excess reactant, and the car bodies completely consumed, completely used, we call them limiting reactant. Whenever we talk about limiting reactant, it means when we don't have enough of them, the reaction is stopped and we can't use many more products. We cannot produce any more products. So there are examples as we see in this slide. How to work with the chemistry. Look at this example. Question says how many grams of silver bromide AgBr can be produced if we have 50 grams of this reactant and 100 grams of another reactant. Look here, question for limiting reactant problems. Always you are given amount of reactants. If we have 50 grams of that and 100 grams of this, how many products we can make? Look at the example I gave it you. If we have amount of wheels, amount of frames, how many bikes we can make? So we are going to do like this. We are given amount of the cars, amount of the tires. We want to know how many cars we can make. And for this example, we have amount of each one, and we are going to know what is the product. So for limiting reactant problems, always we are given two numbers for reactant side. 50 grams of that, 100 grams, which one is limiting reactant? Whenever we say limiting reactant, it means we are talking about only this side. One of these two should be limiting reactant, and another one should be excess reactant. How to solve our problem? To solve our problem, based on the strategy given by your textbook, you need to solve this problem twice. Two mass calculation to get the answer. So two mass calculation. It means we should say if we have 50 grams of magnesium bromide, how many grams of silver bromide can be produced? How many grams of product can be produced? If we start with this. So another example, if we have 100 grams of silver nitrate, how many grams of silver bromide can be produced? We should solve this problem twice. One for magnesium bromide to produce AgBr, one for magnesium for silver bromide to see how much of AgNO3 can be used. These type of problems always called limiting reactant. So I'm going to calculate the mass of AgBr produced from each reactant. We start with this one, magnesium bromide. I'm going to know how much of AgBr can be produced. I write grams of magnesium bromide here, mole on the top. Call it molar mass. You calculate molar mass. So if you calculate molar mass of that, you should get this number. This one and that one cancel out. We have 1 mole magnesium bromide. Right now, I'm going to convert mole magnesium bromide to AgBr. The only way we can convert one substance to another substance is mole ratio. So I have to write mole ratio. Mole magnesium bromide, moles AgBr. Look at the balance equation. 2 moles AgBr and 1 mole magnesium bromide. So this conversion factor, second conversion factor, is mole ratio comes from the balance reaction. This one and that one cancel out. And we are going to know how many grams of AgBr. So we need to convert moles AgBr to grams AgBr. So moles and gram, molar mass, we need to calculate because this is a mass calculation. So if you calculate that by periodic table, you will find this. I ask you to calculate this for me by your calculator and see are you able to get the same number 1 or 2, 3 suffix, 3 suffix. Right now, I say that if we have only 50 grams magnesium bromide, we can make 102 grams AgBr, 102 grams AgBr. We need to solve this problem one more time if we start with 100 gram AgNO3 and see how many grams AgBr can be produced. At that time, we are going to compare our results, and the smaller number, it gives us limiting reactant. Let me solve this problem for AgNO3 and see how many grams of AgBr can be produced. Same strategy, same scenario. grams AgNO3, we should convert grams AgNO3 to moles. We need to use molar mass of AgNO3. You look at the periodic table and calculate that. This and that should be cancelled. Right now I have mole AgNO3. I need to convert to mole AgBr because we have mole. The only way, look at the balance equation and calculate mole ratio. Mole AgBr and mole AgNO3. 2 for AgBr and 2 for AgNO3. These numbers. Right now we need to convert moles AgBr to grams AgBr because we are going to calculate mass. Look at the molar mass. Calculate this. Whenever you calculate that, you will find like this number. For this number, we have 4 suffix, and that is why we reported 4 suffix. We have two numbers now. 102 grams for AgBr and 110.3 grams for AgBr. Always a smaller number, less amount of the product, it gives us limiting reactant. 110 or 103. 102. 102 is the correct answer. Limiting reactant belongs to this compound because it makes a smaller amount of the product, 102. So this reactant, it makes the larger amount of the product. So a smaller number is limiting reactant and larger number, it gives us excess reactant. For this problem, the amount of the product from these two, 102, 110. The smaller number belongs to this reactant, we call it limiting reactant. For this problem, magnesium bromide is limiting reactant, and AgNO3, it makes the larger number. It gives us excess reactant. And if we are going to know what is the exact amount of the product is going to be produced, a smaller number, 102 grams. This is the typical problem that you see for this section. So I may ask you to work on this one and see are you able to get the correct answer or not. Please pause this video. So you just need to solve this problem by writing two mass questions. Mass stoichiometric problem. We have amount of the reactant, and we are going to know how much of the products can be produced. If you solve that, you should have a strategy like this. We start to solve this problem twice. We start with this and see how many grams of products can be produced. Another time, we start with that and see how many grams of products can be produced. So, we start with 200 grams, convert mass to mole using molar mass, using the mole ratio to convert this compound to that compound. 1 and 1. And convert moles of these to mass. So like this one. 3 conversion factors. And the number is like this number. Right now, we have 178 grams of this product if we have 200 grams of barium nitrate. We are going to see how many grams of barium sulfate can be produced if we have 100 grams of sodium sulfate. So we solve that one more time. Right now, 100 grams of this. Same strategy here, you just need to calculate molar mass of this compound, convert to moles, look at the mole ratio, here is same again, and we have the molar mass of that. So you will find 164. For the previous one, we have 178. It looks. This smaller number belongs to this reactant. This reactant is limiting reactant. And the amount of the product based on this number is 164. This number for that one is larger one, we call it excess reactant. I may ask you to read your textbook, look at the solved problems on your textbook. If you have any question, ask me or stop by in the tutor center or watch other videos as additional resources. And last thing, when we work in the lab, we need to know that we predict for this example, we predict in the theory we produce 164.4 grams. But sometimes is the number that we can measure in the lab is not exactly like this one, like we are going to do this in our lab. Based on the errors in your calculation, based on the errors in your rounding, based on the errors in your measurement, based on the purity of the compound, impurity of the compounds, or any other errors like systematic errors, errors in the balance that we cannot control them, errors in our measurement for the volume by reading the graduate cylinder. We cannot make exactly the same number like this. Whenever we are going to work in the lab, we need to know we have one concept called it reaction yield or percent yield. Percent yield, as you see in this formula, it has two parts, actual yield and theoretical yield. First, let me talk about theoretical yield. The number you calculated, like the previous example, you predict. We call them theoretical yield. The number we predict in the theory to produce the amount of the product. But when you work in the lab, in the real chemistry, you make actual number, actual amount of that. The number is a little different. We call it actual yield. The relationship between these two, actual divided by theoretical times 100, we call it percent yield. And we prefer to have our percent yield close to 100%. If your actual yield is close to theoretical yield, it means you have the minimum errors or you have high accuracy on your experiment activity. So theoretical yield, if you calculate like we did for the previous example, actual yield when you work in the lab, always actual yield given by the problem. Actual yield is amount of the product given by the problem. So you are not able to get the actual yield. Always you are given by the problem. So if you have actual yield always by the problem, you calculate by the theoretical yield, by the problems that we did, and the relationship between these two, it gives us percentage. Let me work on one example. Question says calculate the percentage. Calculate the percentage yield of the AgBr if 375 grams of the compound are prepared from 200 grams of magnesium bromide. Look here, I'm going to see which one is actual yield. Actual yield is the amount of the product given by the problem. Which one is a product here? Magnesium nitrate, silver bromide. It says 375 grams of AgBr. Amount of the product is actual yield. So right now I have actual yield. To calculate the percent yield, I need to calculate theoretical yield. I have actual yield. I need to calculate theoretical yield. How to calculate the theoretical yield? Mass calculation. If we have 200 grams of magnesium bromide, we are going to predict how many grams of AgBr can be produced. So mass calculation. You know how to do that. I'm going to have a quick review regarding that again. 200 grams of magnesium bromide, we have gram. First we need to convert to moles by using molar mass, like you calculate from your periodic table. When we convert magnesium bromide to AgBr, we need to convert mole because we are going to convert one mole to another one. So this is the number given by the balanced chemical equation. Then you convert mole to mass based on the molar mass you have. So we predict we have 408 grams AgBr. By the theory, we predict we make 408 grams of AgBr. We call it theoretical yield. Actual yield is 375 grams. If this number is smaller than that one, because we have some errors, we have impurity in the compounds or any other error sources. So you have actually 375 grams divided by theoretical yield times 100. So you will find like this number. You have division 4 suffix on the top, 4 suffix on the bottom, you report by 4 suffix. Percent yield should be a number smaller than 100. Whenever this number is close to 100, it means you are very accurate. So it was a quick review regarding the percentage. As additional information, as always, we have in our video, I may ask you to work on this and see are you able to get the percentile or not. I may ask you to pause the video and after that pay attention to my explanation. Alright guys, question says calculate the percentile of Al2O3 aluminum oxide. For your exam, I ask you to work on the name, not the formula. I give it to calculate the percentile of aluminum oxide if we have this information. Question 7, if 125 grams of aluminum give us 100 grams of aluminum oxide, amount of the product is actual yield. Amount of the product is actual yield. We are going to see what is the theoretical yield if we start with 125 grams. So for the percent yield, actual divided by theoretical, we have actual product. So we start with the original number. We have aluminum, we need to convert to moles. Always we need to convert to moles. Look at the periodic table. Right now, whenever you are going to convert one substance to another one, look at the reaction, balance reaction. 2 moles aluminum and 1 mole aluminum oxide. 2 moles aluminum, 1 mole aluminum oxide. Right now, we need to convert moles aluminum oxide to grams. We look at the molar mass. We need to calculate that. So we predict to have 236.3 grams of aluminum oxide. We predict in the theory, but when you work in the lab, you had 100 grams. So actual or theoretical. So we call this number percent. As you see here, this number is not enough good. It means the person performed that experiment is not enough accurate to make enough accuracy for making the percent yield close to 100%. One other thing that you may have in your textbooks, actual yield sometimes called experimental yield, because you work in the lab, we call it experimental. Alright guys, I just wanted to have a quick review regarding chapter 8. We reviewed this chapter by working on 3 concepts. Stoichiometry, it means we need to find a relationship between amount of reactants and products or any other species. We have 2 types of stoichiometric calculations in this video, mole, and mass. And I may ask you to know the strategy. And last thing, we talk about the limiting reactant and excess reactant. Limiting reactant definition and excess reactant definition should be first understand, then we need to work on the problems. I ask you, if you have any question, please stop by in my office, send me email, or before going to do these actions, stop in the tutor center and watch other videos. Tutor.com, always you will find some other information. Also, we uploaded all in our classes additional videos and resources. You may watch them. Alright guys, take care and see you all in our class.